Okay, right. So we are going to continue with flexible AC transmission systems. Okay, right. We are going to continue. So, right, here goes. The basic thyristerized VAR compensators are the thyristor controlled reactor. Okay, the basic thyristerized VAR compensators. It is basically your TCR and your TSC. Now, here's your TSC, here's your TCR. Okay, your TSC, it is what we call your thyristor switched compensator. Now, long story short, what is this about? Here we are dealing with basic thyristerized VAR compensators. Okay, so we are dealing with what? Compensators. Which ones? Your thyristerized VAR compensators. And in this case, there's two of them, at least for now. Okay, your thyristerized control reactor, your TCR. Okay, now when I say TCR, you hear the word reactor. Reactor just refers to that inductor or coil. Okay, and then you have your thyristerized switched capacitor, which is that capacitor over there with your current choking uh, inductor there, DIDT limiter. Okay, right. Now let's continue now. What do we realize? We realize that you have your TCR, you have your TSC, but there's also a case where you have your your TCR in conjunction with what is called a fixed capacitor. Okay, and that fixed capacitor, okay, when it is included, then we talk about a FC, fixed capacitor thyristerized controlled reactor topologies. So, okay, should just take note of that. And then now let's continue. Over here, we will notice that we have another thyristerized compensator. And this one is referred to as the thyristor controlled series capacitor. Okay, thyristor controlled series capacitor, your TCSC. Okay, the self commutated VAR compensator, it includes the voltage sourced converter, the self commutated. Okay, now why is this important? This is important because of the following. We have what is called thyristerized compensators or VAR compensators. Now, it's actually a thyristerized compensator. The VAR, it just refers to the, let's go back, it just refers to the reactive power aspect of it. That's why we say VAR. It's actually volt ampere reactive or reactance. Okay, right. The basic thyristerized VAR compensator, and then over here you have two, but as you continue you'll notice there's also a case where you have your TCR in conjunction with a fixed capacitor. Okay, and then that's how we end up here, where we now can talk about the self commutated VAR compensator. Now again, why did we have to page back? Because this is a thyristerized VAR compensator. Thyristerized, remember that, thyristerized VAR compensator, and this is a self-commutated VAR compensator. Ooh, I'm hoping that we are learning, okay? Now, the self-commutated VAR compensator, it includes the voltage sourced converters, your VSCs, and current sourced converters, CSC, as well as static synchronous compensators. Okay, static synchronous compensators. Okay, that otherwise known as your, those are otherwise known as your statcoms. Okay, united power flow controllers. Okay, that's your UPFC, and dynamic voltage restorers. Okay, so what do we notice here? We notice there's a line 1, line 2, line 3. Okay, and then we notice that there's some switching here that's happening. Okay, and then we notice that our VDC, it is in this case a capacitor. Okay, that is our VSC. Okay, our voltage sourced converter. Okay, voltage sourced. Okay, right. And then we'll notice there, relative to line 1, we have an inductor, an inductor, an inductor. Okay, and then that's a VSC topology. And then as we continue now, we will notice between line 1 and this here should be viewed as, for now, let's call it an earth terminal. Okay, an earth terminal. Yes. Okay, so between line 1 and your earth terminal, what is it that you have? You have a capacitor. Between line 2 and your earth terminal, you have a capacitor. Line 3 and your earth terminal, you have what? A capacitor. Okay, right. So it's being earthed via a capacitor relative to relative to earth. Yes, relative to earth. And this is what we call our CSC topology. Now, what is CSC? CSC, it is our current sourced converters. Okay, current sourced converters. And then we will notice that our IDC, in this case now, it's an inductor. Okay, now obviously if you struggle to memorize this then this is what I would advise. Okay, the moment we say voltage sourced converters, voltage source converters, what I would state is the following. If we look at voltage in a circuit, what is voltage in a circuit in the context of a capacitor? What is it used for? A capacitor normally builds up what we call an electrostatic field, okay? And then for you to build up that electrostatic field, you need a voltage source, okay? So then the voltage source is the thing that will enable and allow you to induce an electrostatic field between the plates of a capacitor, okay? So for that reason, you need that voltage. So just think of voltage with that association in mind, with reference to capacitors, okay? And then when we say VSC topology, it should make sense to you, okay? Then obviously if here's a capacitor, then relative to your line 1, line 2, line 3, you should have inductors. And then the same thing happens over here. Here we say current sourced converters, okay? Current source. Now, when you think of current in a circuit and you think of an inductor, what comes to mind? The thing that comes to mind is an inductor, it normally builds up what we call a magnetic field. Now, for that magnetic field to reach a level of saturation, to go from 0 to, in this case, let's say saturation. Okay, what do you require? You require that the conductor be connected to a current source. Okay, and then that current source is going to do what? It's going to induce a magnetic field around the coil. Okay, right. And then that association or that analogy, okay, I want you to link it to this inductor. And then obviously if this is an inductor, the inverse of an inductor, in this case it will be your capacitors. So hopefully this should enable or allow you to memorize this in an easier fashion, or at least that's my hope. So yeah, and then let me see. Okay, I'm going to stop here for now.